Hello, and a massive welcome to this explainer. I'm absolutely thrilled you've tuned in today. If you've ever found yourself wondering how the molecular world is actually built from the ground up, well, you're in for an absolute treat. Today, we're diving straight into the architecture of the universe at its most fundamental level. We're talking about chemical bonding. Let's get right into it, shall we?
But before we get bogged down in the how, we've got to ask ourselves a pretty simple question. Why do atoms even bother bonding in the first place? I mean, why don't they just happily float around entirely on their own? Well, the best way to look at it is to frame chemical bonding as this microscopic, universal quest for stability. Atoms are constantly on the hunt for a lower energy state. They want to be stable, and for the vast majority of them, flying solo just doesn't quite cut it. They absolutely need partners to get there.
So here's our roadmap for today's session. We'll start with the quest for stability. Next, we'll look at ionic bonding, or the electron stealers, followed by covalent bonding, the electron sharers, and metallic bonding, the electron sea. Then we'll tackle electronegativity, which is really the deciding factor, and we'll wrap things up with the bonding continuum.
Right? Section 1. The quest for stability. Now, you might already be familiar with the octet rule. Formulated way back in the early 20th century, it's essentially the rule that atoms prefer having exactly 8 electrons in their outermost or valence shell. Think of it like finding that highly satisfying final puzzle piece. The noble gases, sitting smugly on the far right of the periodic table, already have this full octet. Because their orbitals are completely full, they have zero charge and are incredibly stable. They practically never react. So all the other elements are essentially just trying to mimic those noble gases. They're gaining, losing, or sharing electrons just to reach that perfectly stable, low-energy 8-electron setup.
Moving on to Section 2, Ionic bonding, the electron stealers.
Ionic bonds happen when there is a complete transfer of electrons. Honestly, this interaction is the ultimate microscopic theft. Picture this. You've got an electropositive atom, usually a metal, that is practically begging to get rid of an electron to reach stability. And right next to it, you have an electronegative atom, a nonmetal, that is absolutely desperate to gain one. So, the metal just gives up its electron entirely to the nonmetal. This bold move creates a positively charged cation and a negatively charged anion. And, because opposites attract, these two newly formed ions are immediately locked together by really powerful non-directional electrostatic forces. Because of these massive electrostatic forces, ionic compounds end up with some very specific physical properties. We're talking extremely high melting and boiling points, and they form these beautifully symmetric crystalline lattice structures. A brilliant everyday example of this is your standard table salt, sodium chloride. Think about it. Sodium metal on its own is highly reactive, and chlorine is literally a toxic gas. But when sodium transfers its one-valence electron to chlorine, a huge amount of heat and light is released, leaving us with a salt crystal that is incredibly stable and completely unreactive. Oh, and while they're quite hard and brittle as solid crystals, if you melt them down or dissolve them in water, those ions are suddenly free to move around, making them absolutely fantastic conductors of electricity. All right, Section 3, Covalent bonding, the electron sharers.
Let's look at chlorine gas. When you have two identical nonmetal chlorine atoms, neither one is willing to give up an electron entirely. They're both just too greedy. So what do? Their atomic orbitals actually overlap in physical space, allowing them to share a pair of valence electrons. This shared electron density sits perfectly right between the two positive nuclei, holding the atoms together and miraculously fulfilling that octet rule for both atoms at the exact same time. It is, quite simply, the perfect compromise.
Now, because covalent bonds rely on sharing electrons between specific, localized atoms, they are highly directional. This is a big departure from that all-around electrostatic pull we just saw with ionic bonds. And this leads to vastly different physical properties. Covalent compounds, think of the water you drink or the methane gas you use for cooking, typically have much lower melting and boiling points. They tend to form discrete individual molecules rather than massive, endless lattices. Plus, because they don't have those free-flowing charged particles roaming about, they are generally pretty rubbish at conducting electricity.
To really lock this in, let's quickly juxtapose these two distinct bond types side by side. On the one hand, ionic. It's all about the total transfer of electrons, forming charged ions that attract each other in absolutely every direction. On the other hand, covalent. It's all about the sharing of electron pairs through localized orbital overlap, creating a highly directional bond. Essentially, it boils down to stealing versus sharing. It sounds like a simple distinction, but it fundamentally dictates how an entire material will behave in the real world.
Which brings us to Section 4, metallic bonding, the electron C. Now, metals are a bit of a special case. They have low electronegativity, meaning they only hold on to their few outer electrons quite loosely. So when metal atoms pack together, they essentially pool their valence electrons. This creates this incredible, continuous sea of delocalized, freely moving electrons that surrounds a solid lattice of tightly packed, positively charged metal ions. It's like a communal electron glue that perfectly counteracts the repulsion between the cations and keeps the whole structure from just flying apart.
The really crucial takeaway here is how this entirely unique structure dictates a metal's properties. Because those outermost electrons are completely delocalized and free to roam wherever they please, metals boast excellent electrical and thermal conductivity. That very same electron C interacts with incoming light to give us that classic, shiny metallic luster. And quite beautifully, because this bonding is non-directional, the metal ions can actually slide right past each other without shattering the bond itself. This is exactly why metals are malleable and ductile. It's why we can hammer them out into flat sheets or draw them into long wires without them breaking.
Moving right along to Section 5, electronegativity, the deciding factor.
We've mentioned it a few times, but electronegativity is simply defined as the ability of an atom to attract a pair of electrons towards itself within a chemical bond. To put it conversationally, you can just think of it as how greedy an atom is for electrons. It operates on a sliding, dimensionless scale from 0 to roughly 4.1. Elements with low numbers on this scale are more than happy to lose electrons, while the elements with high numbers fiercely want to snatch them up.
We can actually use a very simple, logical flowchart to empower ourselves to predict chemical behavior straight away. Step 1. Identify the two atoms that are bonding. Easy enough. Step 2. Mathematically calculate the absolute difference in their electronegativity values, which chemists often call delta En. Step 3. Just use that absolute difference to predict exactly how those electrons are going to behave. It really is that straightforward. Let's walk through this rather brilliant data table so you can see exactly how the maths works out. If the difference is huge, say greater than 1.7, one atom is so much stronger that it just outright steals the electron. That's your mostly ionic bond. Now, if the difference sits between 0.4 and 1.7, they share the electron but unequally. The more electronegative atom hogs the electrons, pulling them closer and creating a polar covalent bond with partial charges. If the difference is less than 0.4, it's mostly covalent. And if the difference is exactly 0, just like in our chlorine gas example earlier, it's a pure, non-polar covalent bond where those electrons are shared perfectly, 100% equally.
Finally, Section 6, the bonding continuum.
When you chart the percentage of ionic character against the difference in electronegativity, it reveals a smooth S-curve, not some rigid staircase. You see, chemical bonds are almost never 100% purely ionic or purely covalent. A bond actually smoothly shifts from pure covalent character, like the chlorine gas down there at the bottom left, all the way up to highly ionic character, like cesium fluoride at the top right. It is completely a sliding scale.
To fully visualize this, scientists use something called the Van Arkel-Ketelaar triangle. This brilliant model plots compounds on a 2D plane. The y-axis represents the electronegativity difference, showing us just how polar or ionic a bond is. Meanwhile, the x-axis plots the average electronegativity of the two atoms, showing how localized the electrons are. By placing ionic, metallic, and covalent bonds at the three far corners of the triangle, it maps out all the intermediate bonding states perfectly. It shows us, plain as day, that materials can and do have beautifully blended characteristics.
I really want to highlight this powerful quote from our sources. Chemical bonds are not just particular bonds of a specific type. Rather, bond types are interconnected, and different compounds have varying degrees of different bonding character. This completely shatters the illusion of black and white rigid rules we often learn early on. It demands that we step back and embrace the true, continuous, and highly dynamic nature of chemical reality.
So I want to leave you with a bit of a provocative thought today. If strict bonding categories are actually just a continuous, interconnected spectrum, what other supposedly rigid scientific rules might just be beautiful sliding scales? Science is rarely as simple as checking a box. Keep questioning, keep exploring. And hey, for more science tips and tricks, make sure to follow us. You can contact Academic Zenith Online Academy right now to book a free demo class and avail a 30% discount on absolutely any course. Cheers for watching, and I will see you in our next explainer.